Hi all. Hi all. I'm Hannah. I'm a program associate at the Mozilla Foundation, which is committed to building alternative digital futures through a number of ways, this being one of them. Um, and I'm excited to introduce Alessandro from Unitary Foundation, which has been working at the intersection of open science and open source quantum for a while. They do a number of things, from microgrants to research to building community around open source quantum tech. And I'm excited to introduce Alessandro, who works on quantum benchmarking at the Unitary Foundation. And before that, he did research in quantum information theory and spent a decade building both proprietary and open source software. So, Alessandro, I'll let you take it away.
Thanks, Anna, for the introduction. Let me share the screen. All right, you should be able to see the slides.
Looks good.
Yep, cool. Yeah, so what I want to talk about today is part of this collaboration between the Mozilla Foundation and Unitary Foundation. I want to talk about why we believe that quantum computer benchmarking should be open and accessible. So Anna has already introduced me, but maybe very quickly, I'll just say a bit about my overlap with Mozilla. Been a Firefox user for 15 plus years now. So honored to be invited to give this talk. I mean, that's probably something I share with many other people, but something a bit more niche. I was also a Firefox OS user, for those who remember that. That was somewhere around 2015. That was an attempt to make a web OS for the phone that was quite cool by Mozilla. And as part of that interest in Firefox OS, actually, I was also mentoring a Mozilla outreach project again in 2015. So yeah, my path has I've already crossed the Mozilla Foundation. So enough about me and maybe a bit more about the Unitary Foundation. As Hannah said, it's 501c no profit, which tries to make quantum tech and quantum science more open and accessible. We do run a microgrants program, which you can check out on our website, unitary.foundation. Also, Vina, who is in this call, and Ben on May 6th are going to talk about that. We basically fund contributor to quantum open source and quantum tech in general. We had lots of success running this program for the last 5 years. We also do research in quantum software mostly, areas like benchmarking, which is what I'm going to talk about today, compilation, and quantum error mitigation. Some of the research team members of Unitary Foundation are in this call as well. And finally, we have a big community around it. We like to think it's making a big impact in open source quantum tech. We have a big Discord server that you are welcome to join to hang out and talk about open quantum science. We run like some hackathons as part of community initiative. We run a conference usually in the summer for open source quantum software as well. But again, about this and other things, Unitary Foundation related, there will be 2 more talk. The second one is on April 14 by the Unitary Foundation President Will. We'll talk about the impact of open source quantum in general to the ecosystem. So let's talk about the main thesis of this talk, which is, in my opinion, and in our opinion, in classical computing, in classical tech in general, we could work with a proprietary benchmark. Not ideal, of course. We would like to have everything open and transparent in every field of our life, but we could survive with proprietary benchmarks. Whereas the thesis is that in quantum computing, we really need open benchmarks, at least at this stage. So a bit about classical benchmarking. Here by classical technology, I mean the broad set of like computer systems that are not quantum, and all the things, as well, all the software, all the things that you can run on top of these machines. So one important properties of those is that since they have evolved in a long history, about, I don't know, 70, 80 years now, the systems have converged to architecture and implementation that are quite comparable with each other. We still have, new things like recently GPU, or well, by now not so recently anymore, but maybe TPUs. But within TPUs or GPU or CPU, things are quite comparable with each other. The access to the systems is also fairly easy. So, you can buy a laptop for like 300 US dollars, and you can run things at home. Or if you want to run larger things, you have access to cloud systems that are not that expensive nowadays. Moreover, you can actually run real world applications, as you all know, like we all use computers and we run things that we actually need on our everyday life. And finally, there is lots of history of benchmarking as well. So there is a constant cross-checking between different benchmarking tools. So if one benchmarking tool is not really satisfying for some needs, then something else will be covered by another tool, and you can cross-check the results. You can say, there must be something wrong with the version of this tool because it's not coherent with this other tool. And they are quite standardized by now. So I'll give some example of these. So yeah, the thesis is that the fact that benchmarks are widely used and by now trusted, they have lots of ground and history. They don't necessarily need to be open, although we all would prefer to if they were open. So some examples, you may be all familiar with Geekbench. You can go on geekbench.com, download a software that you can run on your machine, on your MacBook, and it will give a score to the CPU that is on your MacBook or the GPU. And then you can upload these results, and this will belong to a data sets of all the benchmark results that were collected using this tool. And Geekbench is actually, as far as I understand, the software is proprietary, but again, it doesn't matter too much because you can actually match with real world tests. If you buy a GPU to play your favorite game and then you bought it because Geekbench dataset was giving it a high ranking, then you can actually play the video game and see that it's not lagging. It's actually working as you expected. We have a long history of benchmarks for much bigger systems, like the top 500 supercomputer are ranked by problems that are usually related to simulations, to linear algebra, to like numerical simulations. And you can actually go to top 500.org and see how those supercomputers around the world rank. Even there, the LIMPAC is an open source suite of numerical tests, but each of the implementers, each of the owners of those supercomputers have some system-specific implementation, and sometimes there is not like full transparency on what is actually running, because you can actually check the results at the end of the day. So more recently, of course, we are all hyped up by AI, so we definitely need to understand which model is the best. We do have, as I said, we can benchmark not only the machines, but also the things that run on those machines. In this case, large language model can be ranked based on some specific test of real world applications. And this Epoch AI is actually a cool website where you can find sort of a meta collection of those benchmarks, all with a composite score, which is this ECI ranked, but also ordered in a time series. So you can actually see the evolution of the score and in general, the evolution of the field, which is quite important for the field itself. And they also have more frontier benchmarks. So we can actually understand things like how close we are to, human intelligence or even superhuman intelligence and things like that. But not much controversial. There is some controversy about which benchmarks are more suited and whatnot, but you can sort of aggregate it in this way, and most of the people will agree this Epoch AI composite makes sense. We also can do this on modern ML stack, which are the hardware stacks and software stacks that run those models. There is a website called MLPerf and an organization called ML Commons, which aims to classify machine learning stacks by benchmarks that are actually inputted by the users. So users are organized in working groups, and there are like rounds of benchmarking. As you can see from the screenshot, that was like run, I think the latest one was round 5.1 for training benchmarks. And those results are uploaded in batches, and you can go and actually rank the device by that. Again, here the specification of the benchmark are public, but the implementation is mostly left to the users. Something maybe closer to Mozilla and to web developers in general, if there are any on this call, or actually more to like browser developer. You may be all familiar with Browser Bench. As far as I understand, that's actually open and transparent, runs lots of tasks on your own browser, and you can check the score that you get at the end. And actually, while I was looking for a screenshot of Browser Bench, I stumbled upon this from the Mozilla blog in 2017. Assuming the quantum that is here is not really the quantum I'm going to talk about, but it's interesting that they did use pedometer, which is the Browser Bench suites of benchmark to improve the performance of Firefox in a new release by 2 times. And yeah, so just to be clear, we are not able to yet run browsers on quantum machines yet. So that was a classical technologies benchmarking. Again, the thesis there is that it's quite solid by now. It has lots of history, and because of many reasons, you can trust benchmarks that don't need to be necessarily open. They are sort of semi-open with like specs that are fully open, but maybe implementation that are not. And some of them are even proprietary, but we mostly trust them. So I will not go through quantum computer 101 intro. I will not explain how they work, but I will not even assume that everyone knows how they work. I will mostly base my talk only on abstract concepts that, yeah, you will see in the next slide. So the first important question in quantum is, what do we even benchmark? So it's a completely new full stack system from the top to the bottom. So we are rewriting, when I say we, of course, I mean the whole quantum computer community are rewriting each single layers, starting from the language, the programming languages that we use to write software, to the compilers, to optimizers. We still need error corrections, which is something in classical computer we did decades ago. We need to map those error-corrected, compiled programs to hardware. We need to run those once they are mapped to hardware. We need to run them through possibly some classical firmware that controls the hardware. And eventually we can finally run them on hardware that on its own, it's more complicated than what you think, than what you may think, if you are not too familiar. One disclaimer is that I'm not too familiar with the actual implementation of the hardware itself. I'm mostly, so I have a software and theory background, but you can see that's a diagram from the NVIDIA vlog. So NVIDIA is one of the players in the quantum, in the race to build a quantum computer. They mostly develop software, but this is a diagram from their blog. I don't know if it's originally from them, but you can see the QPU, which is the quantum processing unit, is only like a really small part of the whole quantum computer hardware. So the question becomes, what are we really benchmarking? So ideally, we want to benchmark each single layers of this stack to make progress on each of them, but also holistically from the user point of view. What really matters is like how good is the whole machine in running their application. So even these basic questions is way more complicated than in the classical situation. So to make things much more complicated, the QPU that you saw at the bottom right in the corner on that diagram, which was on its own at the bottom of the stack of the computer, can be realized in different way. In fact, the qubit, which is the smallest unit of information that you have in quantum, can be realized in a different physical way. Like you can encode it in a single atom. In the photonic case, you can have a photon. It can occupy, for example, two optical modes, and then you have the equivalent of 1 and 0 in a bit. But that's only one way to implement it. You can have it encoded in atoms, but also in more complex systems, fortunately, because maybe those are easier to handle since they are like physically bigger. You can have like a superconducting circuits that act in a way so that you can have quantum mechanics situation up and there, and you can encode a qubit. So these are like four modes of how you can realize physically a qubits, but there is even more than that. And for each of these modes, you can have orthogonal axes in which some of them are better than the other. So as of now, there is not a clear winner. And many groups around the world, many research groups from industry and universities are trying different things, are trying the superconducting approach that I was proposing. That's mostly IBM, Google, IQM, and others, which are very fast compared to other, still slow compared to quantum computers in terms of operations per seconds, but quite fast compared to other modes. However, they don't have the highest, what I'm calling here fidelity. You can imagine is like the accuracy, so the sort of the opposite of an error. So they tend to have more noise, to have more error than other modes, or rather like medium level of errors. I didn't list all of them with pros and cons and different axes because that's one of the goal of a benchmark of the benchmark program in general. There are other axes that are just as important as speed and fidelity, pricing, of course. So it may be that you are able to come up with a technology and a physical realization of a qubits that is very fast and has very low error, but is incredibly expensive and nobody can afford it, in which case it's useless. Or you can have a technology that for which you can build maybe 10 qubits, 20 qubits, but it cannot scale above that. And that's also very important. So the place where we are right now, in 2026, we still have quite small systems. I was generous here to use the 1,000 numbers, but we are more around like between the tens and the hundreds of qubits. And for those who are not familiar with quantum computer at all, I'm not talking about like the size of a register here. I'm talking about the full memory of the system. So yeah, it's not like playing a 64-bit console and that has 64-bit registry. This is actually the full size of the memory that you have. In fact, we don't even have a distinction between different kind of memories yet, because we are still at this regime, which is very small. Still exciting because you can start to run experiments that is not clear if you can run on classical computer, which is what we call quantum advantage. So we are starting to see, especially in the last couple of years, early signs of that. Unfortunately, the machines are still quite noisy, so full of errors that one needs to correct or mitigate in some way before getting an output. And because of all of these things, we don't really have yet real world applications, not even in quantum chemistry or this more promising one that you can just run easily. So in terms of benchmarking, you cannot just, you may all know that one reason why quantum computers are exciting is that you may be able to factor a very large number in much smaller time than you do with classical computers. But at the stage where we are now, you cannot just throw the number there, ask the machine to factor, and then check the result and see if the product is actually the number you wanted to factor. And you cannot time it. So that would be the equivalent of the kind of benchmarks that we have in the classical world, like in the the Geekbench equivalent would be you own a quantum computer at home, you ask it to factor, you measure how long it takes. The smaller the number, the better. But we cannot do that yet. One important thing, I already mentioned pricing. Hardware at the moment is very expensive. There are few machines around the world. This is an estimation of pricing I got from the originqc.com. That's one of the Chinese quantum computer builders. This is a blog post from last year. This is the sort of, it's a very average slide, very average, like very average numbers based on all the technologies I was talking about and all the things that exist right now. But pretty much the initial cost of having something like that in your lab would be $5 million. Operating it would cost $2 million every year. Even if you are just renting quantum processing unit time from the cloud, clouds like AWS are already offering it. The initial cost may be zero, but then for the kind of experiment we want to do right now, or you may want to do in a small, say, quantum chemistry lab, that would be around, again, being generous, about 100K of US dollar per year. So we are talking about very expensive machine, and that's one of the challenge of making them more accessible, because every time you run a benchmark, you are going to pay that money. So as I mentioned before, this is a small recap. We have multiple physical systems on which you can realize the qubits. And what I didn't mention before is that even when you want to connect multiple qubits, one from each other, because obviously you want them to communicate, if you have more than, if you have an algorithm that is non-trivial, you can lay out them in different architecture and different connectivity pattern and different research group, different players are trying different things. Here is not clear which direction is going to win. So we do want to benchmark at this moment all of them. We are not yet at application scale. I think that point is quite evident. We are approaching quantum advantage. We see early signs of that, but we cannot yet run things at application scale. We are probably not that far. The consequence of that is that there is not a very standard and agreed upon suite of performance metric that everyone says, okay, let's just run those and everyone will be happy. So, and that's probably the biggest challenge. Notice also that the main goal is different. When you run Geekbench, when you run, let's say, Browser Bench to test if Firefox is slower or faster than Chrome, is because you want to make a very short-term decision. Should I install and keep using Firefox, or should I use Chrome or another browser? Same when you are going to buy a QPU to run, a GPU to run your favorite video games or your favorite machine learning model. Here, the goal is slightly different for now. Soon is going to be similar. Is going to be which quantum computer runs some specific application faster or better than the other. But right now, the main goal is actually making progress and then understand if any of these directions are going to the right way, is to understand in general how the field is progressing. And it's still very much research oriented. So I wanted to make that clear. So the current so it doesn't mean that Um, Nobody does benchmarking in quantum because of this challenge. Quite the opposite. It's a very alive field. It's a very hot topic right now. Um, there are lots of vendor-specific tools. This is because each vendor want to understand if they are making progress with their own technology, with the things that they are building. So in order to do that, they are building benchmark protocols and benchmark tooling along the way. The fortunate thing is that they are also exposing this to the public. So some of those screenshot on the bottom right, you can see here are actually GitHub repositories of suites of benchmarks that are by vendors or by research groups that are made public to everyone. In fact, I must say that one interesting thing in quantum is that since we are rewriting the full stack after the, let's say, the open source revolution with Linux being very successful and all the tooling that we use, the open source tools that we use every day, we sort of learned the lessons that we should build as much as possible as open source. Most of the firmware and hardware are still closed, but grand part of the stack is fortunately already open source. We do have a quite fragmented ecosystem in terms of benchmarking, with lots of people believing different things, believing in different performance metrics, arguing on a weekly basis about which performance metric is better than the other. There is lots of research paper. If you go to Google Scholar and look for quantum benchmarking, you will find. I haven't done that search recently, but I'm sure it's in the order of the thousands. And yeah, of course, there is no standardized cross-platform data set yet. I underlined static before research papers because one thing that happens very frequently is that someone, a researcher or a group of researcher comes up with a very interesting protocol or a very interesting performance metric. They run them on 2, 3 machines from like 2, 3 players. They write their paper, they post their paper, they publish it on Nature, wherever, but then that's about it. That's where it ends. Nobody's running really that continuously, and because of the reasons I explained before. So the argument and the thesis of this talk is that not only we want open source protocols, which sort of we already have for quantum benchmarking, but we need a full open benchmarking infrastructure. We need the protocols, but we also need all the tooling around it. We need a very comprehensive or more comprehensive than what we have now, data sets for cross-platform checks. We need a way to think about the workflow end to end, including reviewing the results, the benchmarking results in a more open and accessible way. And in fact, the bonus thing we would like to have is also a full stack open source quantum computers. There is some effort to build, but we are not there yet. That would also be yet another mechanism to improve benchmarking. This is a paper that made that argument. It's called The Economics of an Open Source Quantum Computer. I highly recommend it. It's an easy read, but an important one if you want to know more about open sourcing quantum. So what we need, as I said, apart from open source protocols, is accessible tooling. We want to run the same protocol on all those machines that are by AWS, by IBM, by all the hardware vendors in a comparable way. We want it to be accessible in terms of cost as well, so not prohibitively expensive. because ideally we want to run them continuously over time and track progress of the field and of how the single technology is doing. And in order to make them comparable and reproducible, we want everything to be well defined and the parameters to be well validated. And we need to make sure that everyone is running really the same thing semantically. So by running a protocol here, really, I mean like a very small piece of quantum software and dispatching to one of those machines in the clouds, or if you are lucky enough to have a quantum computer in the lab on site, and then checking the results and timing how long this result took. What we also need is open datasets. We need to have it transparent somewhere where everyone can find it and use it to analyze it. They can split and dice the data sets and do their own analysis. They need to have all the meta data that is required, all the, let's say, error uncertainty to make it statistical relevant. They need to be in formats that are really easy to reuse and to, again, operate if you want to run the benchmark again or run the benchmark against some other machine. So the workflow, as I said, is something we would like to have open and accessible as well. You define a protocol, you implement it, hopefully in an open source repositories where everyone can see it. You run it, you share the results to the community. The community gives you feedback on those results and maybe spot some bugs or some things that are not accurate in the protocol, and then you redefine the protocol, and this creates a flywheel that we believe can foster the space. So at Unitary Foundation, we are making an attempt for a platform that is open and accessible for benchmarking quantum computers, which we called Metric with a Q. And it consists of three main components. One is a Python tool to actually run those protocols in the cloud. So you can rent some, or like maybe if you are lucky, you get some free credits to run quantum software on one of those cloud providers. Then you can use our tool, which is fully open source, and that you can check on this github.com/unityfoundation/metricgym. You can run the protocols just by running the CLI. We may be able to see a small demo of that. We are building we are running this ourselves. We have been lucky enough to get some free credits from different hardware builders and cloud providers. So we are building a data set, which, as far as we know, it is already the most comprehensive cross-platform data set of quantum benchmarking results. And we are building a website to visualize that and to give sort of like a view on these data sets, which is, again, all open source. So starting from the first tool we are building, as I said, it's Python toolkit you can install from PyPy. It's built on an open source software development kit to interface with the different cloud providers and hardware providers. And you can interact with it through the command line. So you can install it, you can define your favorite suite of benchmarks, and then you can run this suite with a simple command as the one you see here in the screenshot. And there are some other cool features, like all the parameters of the suites get validated so that we guarantee that everyone runs the same thing. The user doesn't need to wait on those queues. So something I didn't mention in terms of accessibility is that sometime when you want to run things on a quantum computer, you need to wait even for days because these are devices that are like there are not many in the world. They are very precious, and the time of those is very precious as well. Along with that, we did build our own suite of benchmarks. It's a mix of more system level benchmarks, so more lower in the stacks I was showing before, as well as more higher in the stack of application-inspired circuits benchmark. They are all in Qiskit, which is one of the programming language used to write quantum circuits, but they are easy to translate in other programming languages. And yeah, you can check the suite. I didn't go into the details here of what these protocols are. As far as I remember, we have 8 of them. You can check their implementation line by line on the GitHub repository. The dataset is accessible on GitHub at Unitary Foundation /metric data. We decided to use simply Git as a storage layer so that we didn't have to rebuild the wheel. So we had everything like version control, data transparency, and authentication out of the box. That's an example of one of the results that we got on the IBM Boston machine. Their machine are named after cities. We ran that on the 16th of December, as you can see from the timestamp on the screenshot on the right. It's a protocol with an intimidating name, wormhole-inspired teleportation, but it's actually fairly simple circuits, which can tell you a lot about how the device behaves when some qubits are waiting for other qubits to do their job. Yeah, that's an example of an open and reproducible data point, and there are many of them if you just browse through that repository. So the workflow is quite simple. The workflow we envision. If you are a developer, you can contribute to. So that's the swim lanes at the top. You can contribute to metric, either of the metric gym runner or the suite, and you can propose new feature. You can fix bug, and then as metric core maintainer, we can have a discussion and approve through simply GitHub pull request. So this is all it's all classical software written in Python. So really everyone can contribute to that. We plan to have a more established working group that will decide which protocol should belong to the suite and which parameters should be picked in the schema of each of these protocols. And as I said, everyone can run and upload their results as long as they have access to quantum hardware. And in fact, we encourage people to collect as many data points as possible and share them with us or with everyone. And finally, we have a website, which is, you see a screenshot here, but you can actually go on metric.info, where we visualize a processed version of the data sets. We aggregate them by device or by benchmarks, and we normalize them because each of the protocols may have different unit of measures. So we normalize them, we aggregate them, we show them in a leaderboard. You can see the single results, and you can see something like those epoch AI graphs, how the field is evolving or how each device is improving over time. So I will keep the demo because we are running out of time, but you can see actually a screencast here. So this is how the benchmark parameters are defined. It's simply JSON file, in this case, 3 line. Then you run the CLI command to dispatch the job. In this case, I'm doing it to IBM Torino device on the IBM cloud. I believe it's a 156 qubit job. Um, it's actually, there was no queue, so I finished quite quickly and I'm able to pull the result right away. And you can see this is actually the same benchmark, the same data point I was showing before, but on a different machine. All of this is in a preprint publication that we put on the archive a week ago. So you are very welcome to go and have a look and send us feedback. So what's next is we do believe in this project. We do believe in open and accessible quantum benchmarking. So we hope that this will gather together different research group, different projects from the ecosystem, and trying to unify them. Like we want to keep the diversity these projects are bringing on, but we also believe there is too much fragmentation at the moment. We hope this tooling will get more adoption, so we plan to have more integration with other providers and vendors, but even simpler thing, we want more users to actually give us feedback and run it or create GitHub issues, pull requests around it. We want, in order to do that, we do understand that we need to make the platform even more trustworthy. We already believe it's quite trustworthy, but the more the better if you want to increase adoption of something that will produce results that are quite delicate and important. And finally, we want to work as we get to application level uh, realization of quantum machine. We want to get to benchmark that are more and more complex and closer to real world scenarios. So we want to do all of this while still keeping it open and accessible for the community. What can you help with? As I said, all these tools are written in either Python or TypeScript, so there is nothing too magic about it. For some of the issues that there are on the GitHub boards in this repository, you need to know some quantum, but you can also do lots. You can also help a lot without knowing any quantum at all. Just maybe you are a backend software engineer, maybe you are a designer. You can help us build a better experience, or even better, if you are someone who has experience with classical benchmarking, who has worked on, say, Browser Bench on one of those tools, we really like to hear your experience. Maybe you can share it with us so we don't repeat the same mistake. We do have an umbrella repositories that will lead you to all the other repository, which is at Unitary Foundation /metric on GitHub. I will share these slides, but you can also go right now and take a look, and that will point you and dispatch you to the sub-repository of the platform. So that was everything. Thanks for your attention. And yeah, as a reminder, we have 2 more talks in this series, one by Will on April 14 and the other on May 6 by Ben. And, yeah. Thanks, everyone.
Awesome. Thanks, Alessandro. We do have a few questions in the chat. I think we have enough time and few enough questions that we can have them come straight from the audience. So, Peter, you had a couple questions. Did you want to kind of summarize those for Alessandro? And you can come on audio and video if you're comfortable.
I can also read them up if they are not comfortable.
No, no worries. Yeah, Alessandro, go for it.
So my first question from Peter is saying, my first question, are we concentrating on QASM, QASM versus all other aspects of quantum computing, annealing, and yeah, so we are, don't know if I would say QASM versus annealing, but yeah, we are mostly focused on in our platform. I mean, the talk was quite generic and abstract, so you could apply the same concept to quantum annealing and other aspects, but it's right that we are concentrating in our specific tooling on gate-based model computation. Second is actual quantum computers versus simulators. I don't know exactly what this is referring to, but the tool work for both actual quantum computers and simulators, as long as you have, the API keys of those computers in the cloud, or you have a computer on site. For simulator, third question, do we test actual compliance or do we measure deviations from quantum computers? E.g. breaks the no-cloning theorem. So the tests obviously depend on the protocol. So we do have, at least at small scale, we do have some ideal expectation of what the results should be, and we try to compare it with that.
I think the
I guess
next from Nate.
the next one is a comment. Yeah, I was put into that a brief manual survey of which I was familiar. The only one I don't see is NIST BenchQ. Yes, missed lots of them. It was by far not a comprehensive slide on all the benchmark tools that exist at the moment. The first one that were open in my tab, that's what I screenshotted. But there is much more. There is, BenchQC as well as many others that you can see a partial review in the introduction of our paper on the archive. Maybe I can leave the archive link on the chat. Nate, you want to? No, actually, there's one more comment by Peter. One of the challenges is that everyone has their own interface. Yeah, exactly. That's one of the that's one of the accessibility challenge, and perhaps the main reason why we are building all the tool we are building, so that everyone that you can run things easily across different programming interface, different API, different set of metadata, and so on. Yeah, and that's exactly what I mean by tooling. The next one are from Nate. Nate, do you want to read them yourself?
Sure. Like I'll go the opposite order. So I guess one of the things that seems really beneficial about Metric is that you've built this tool to run circuits on a variety of hardware platforms, which is something that I think more people would like to do, but it's very difficult. I'm wondering, like, do you see value in the tool that you've written beyond just Metric? Like, would you ever think about splitting that out, or is that like not really a goal? And I mean,
Beyond benchmarking, you mean?
yeah.
I personally don't want to take it that direction, because, as I said, we are building it based on the QBraid SDK, which is a layer to do exactly that in a more generic way. The contribution we are bringing is we are making custom, let's say, plugins or add-ons to QBraid specific for benchmarking, and we do want to focus more on benchmarking rather than in general running things across machine.
No, it makes sense.
But we are upstreaming some of the ideas that we get along the way to QBraid. So that's definitely beneficial for the community at large.
And then one other question, thinking about like as metric scales and as you start getting tons more data, like can you stay on Git as data storage forever, or do you have to figure out something new there eventually?
Yeah, I think we are very, very far from Git complaining that we have too many data points. Like the scale here is really, really small. Like because of the pricing and the accessibility problem, I don't remember exactly how many data points we have now, but they are like hundreds of order of magnitude less than what will fit in GitHub in Git storage. So yeah, no plans to do that. There is also not much need to process the data really, really fast. You know, you don't have real-time pipelines that you need to build as you would for Netflix or something like that. So I think when there will be that need, we will probably already have a real-world application in quantum computers. So it's far or close up to you.
I think we have one final question from Korean, if you want to ask Korean, or we can read it out loud too. And this should be the final question just for us to stay online or stay on
Yeah,
time.
I hope I am audible.
Yes.
Yeah,
Yeah. Yeah, thanks, Alessandro, for the session. My query is this. So I saw your website on this metric, which shows the benchmarking of various quantum hardwares. So I want to understand, is there a kind of benchmarking against the various quantum softwares like Qiskit, etc.? Because
very good
say,
question. Yeah.
yeah, so many of this actual performances depend upon the classical transpilation which happens or similar performance, right? So just want to understand whether any benchmarking presently exists or not.
Yeah, good question. So everything we built so far is mostly tailored at the lower part of the stack. So at least at assessing the lower part of the stack, which is the actual hardware. But you are right, there is a bunch of consideration that one should do throughout the stack. First of all, starting from the compilation packages that you're using. So I mean, there are two things here. One is we should also assess the software itself. That's something projects like Benchpress are doing for compilers like Qiskit and Cirq. It's a project by IBM that you can look up on GitHub. You are probably already familiar with. That assesses simply how quickly the classical software for quantum compilation works. But the second aspect here is that you should also take into consideration all these other layers when you are running protocols from the software to the bottom layer. And that for that kind of consideration, I'll actually refer you to the last section of the paper where we have a dedicated explanation. But that's definitely an important future direction. So this tooling, to be clear, it's only at early stage as well, and that's one of the important direction we will focus on this year. So yeah, you are welcome to contribute there.
Thank you, Alessandro.
And thanks, Vina, for sharing the
Awesome. Yeah, we just
link
linked
to the paper.
in the chat. We do need to hop off just to respect everyone's time, but thank you so much, Alessandro, for the talk. Thank you, Hannah, Ziad, and the Mozilla Foundation team for working on this with us, this talk series. And as Alessandro mentioned, we do have two more talks coming up, one in April, one in May. We'll keep blasting those out to the community too as reminders to you all. So thank you all for coming and bringing questions, and we'll see you at the next one.
Thank you. Bye.
Bye, everybody.